Okay. So good morning, good afternoon for you, everyone. I will resume the discussion and the presentation from the slide that we left yesterday, where we introduced briefly the use of failure criteria and their implementation in design processes. And after this, we'll come to discuss, actually, regarding to this slide, we'll come to discuss about this specific point here that is related to failure criteria. So probably you all know, since you are involved with composites, that several criteria have been introduced in the past for the implementation of the anisotropy in calculations related to failure. And one of the first failure criteria that has been introduced for composites is this one from Robert Hill in 1948, that is actually resembling the von Mises theory for metals. And as you see here, what we already discussed is that this failure criterion is considering all the stress components of the stress tensor. So sigma 2, sigma 3, sigma 1, and the shear stresses sigma 4, 5, and 6. So actually, this is what we introduced yesterday, an interaction failure criterion. The components F, J, H, L, M, and N are the failure components that can be defined by simple tests along the X, Y, and Z are the principal normal directions, and R, T, and S in this criterion are the shear directions of the anisotropic material. So later on, if we want to go to the plane stress, we can assume that all the stress components after 3, 4, 5 are 0, and only sigma 1, sigma 2, and sigma 6 remains, which are the two normal and the shear stress in plane. And if we do this substitution in the equation, we end up with a simple equation of this type here, that you can also imagine that can be defined as an equation by simple tests. A tensile test at the fiber direction, a tensile test transversely to the fibers, and a shear test for defining the material properties. And this equation can be used to estimate, according to the implementation of this criterion, to estimate the off-axis stress at any angle theta if we consider the tensorial transformation of stresses. So imagine if you have only a material that is loaded only with this load in an off-axis angle, then the principal stresses, or the stresses in the local system of the material, so along the fibers and transversal to the fibers, can be calculated by this simple equation, where M and N are the cosinus and the sinus of the angle theta that is characterizing the off-axis direction. So if we solve this equation actually for sigma x, we have this simple equation that gives the value of sigma x as a function of the material properties x, y, and s, and the off-axis angle that we have in any case. So the use of this criterion is very simple, as we said. With this simple equation, we can estimate the off-axis strength of a material system, a composite material system. And what is interesting to see in this slide here is that depending on the material anisotropy, we can imagine, we can estimate with this criterion the drop of the stiffness and the drop of the strength. Here I show the strength of a material with the angle theta. And what is interesting to see that for highly anisotropic materials like the one that we selected here, this is a carbon fiber reinforced polymer. we see that only for 2, 3, 4 degrees of misalignment or off-axis angle, we have a significant drop of stiffness. At 5 degrees, in this calculation, we are less than half of the real of the material properties are at 0 degrees. And this is an indication of the sensitivity that we have with composite materials and the patience, if you want to call it like that, that a manufacturer should show when they lay up the material configuration. If you just do a slight misalignment because this day you're not very happy, you are not very consistent with the manufacturing, you can cause problems like that. You actually build a material system that it is assumed to have very good properties, and at the end of the day, it doesn't have good properties at all. So after this Tsai-Hill criterion, more sophisticated criteria have been introduced, and the idea was to consider also in the calculations the interaction of tension and compression. If you remember Tsai-Hill criterion, I'm going briefly back, considered only the tensile failure at X, at Y, at Z directions, and didn't talk about negative force, or what we call in composite the differential between the tensile and the compressive strength. So later on, after this Tsai-Hill, we have the introduction of this failure tensor polynomial. So a lot of criteria have been introduced in this concept to consider also terms. This F12 term is related to F11, F22. These are the similar terms that we've seen before, but F12 and F13, F23 are called the interaction terms, and they are functions of the material properties and can be defined differently. So I will just open all this to discuss. As we said before, for the main terms of the equation, so F11, F22, and so on, we can do simple tests and estimate F11 as the inverse of the product of the tensile strength, X, and the compressive strength, X prime. F11 is this. F1 is 1 over X minus 1 over X prime. So you can automatically see that for a material that does not show different properties in tension and compression, imagine that we have a material that is showing this behavior, tension and compression, this term automatically becomes to 0. And this term becomes like the term of the criterion of Tsai-Hill, like that, equals to F11. So this criterion actually, as you can see, it's a generalization of the criterion that we've seen before. The part that is additional is exactly these 3 terms that are defined by different ways. It's very difficult. So these terms correspond to biaxial loading, actually. Loading between 1 and 2, or 1 and 3, or 2 and 3. So it's very difficult to do this kind of test. That's why we've seen, in a lot of cases, different approaches for these terms. First of all, Tsai-Wu, so Tsai and Wu, in their paper in 1971, suggested to calculate these terms by this equation. Tsai-Han, so the same Tsai with another professor at the time, suggested to calculate the interaction terms by this equation. And then another group of people suggested to neglect these Fij terms because they are very low in value, so it doesn't make any difference. Wu and Stakulski, another group, suggested to calculate these terms by these equations, and so on. And it was other empirical suggestions to calculate this Fij by taking into account all the different components of the material system. So the question here might be, which one of these is best? And the response is the same response that we gave when we were discussing the best SN curve that has to be used. So the best selection here is only related to the material data. So the best configuration is this one that fits better the material behavior. What we've seen with experience is that simple terms like this one, it is sufficient to fit most of the material systems that we have. So, as said, experimental evidence is the only criterion. We have in the past we've seen a lot of results. This picture is taken from a paper from Wu already in 1974. So this is 50 years ago, where they presented experimental data from biaxial testing of composite materials and fitting these materials by different equations. So the first is by the tensor polynomial, so this interaction failure criteria that we are discussing today. The second is by maximum strain failure criterion. And the third one is by a modified von Mises and Hill failure criterion. And if we observe these three plots, I would easily say that this one is the most appropriate. So this ellipse that is defined by the failure tensor polynomial is the most appropriate to simulate this data set. So this is how we can evaluate the selection, or we can evaluate the potential of failure criteria to estimate correctly the material behavior. So how we use the failure criteria in design? Actually, the failure criteria, if we see them in the space, they define a safe area. Imagine this egg here, if you see it like an egg. If you're inside this space here, you're safe. Your material will not fail. If you have a combination of stresses outside this, then this is defined as failure. So this is how the failure criteria are implemented in design approaches. So until now, I discussed about the implementation of failure criteria in design, but we didn't say how we use this failure criteria or what kind of failure criteria we have for fatigue. And if I go there, you see that, again, when we talk about fatigue, we have the same failure criteria. Again, in fatigue of composites, we have failure criteria that are related to this failure tensor polynomial. But there we have to discuss and implement the number of cycles. And we have, in the past, several criteria that have been introduced in this sense. So again, here you see this is kind of an ellipse again, or this is a circle. It's not an ellipse, actually, where we have the material properties in transverse normal and shear. These are defined in this equation. And there is also another equation, simple equation, that is relating the fatigue stress along the axis to the maximum stress at static loading. So actually, this criterion from Hassin-Rotem assumes that the material can fail in two discrete failure modes. There is one failure mode that is related to failure of the fibers, and it is described by this first equation. And there is another failure mode that is related to the matrix, and is described by this equation. So depending on the failure mode, you have to use, according to them, you have to use a different equation. And there is also in their criterion a definition of the angle that the material should the angle that defines, if you like, the switch from one failure mode to the other. So the criterion is defined by these two equations. The angle that defines when the mode switches from failure of fibers to the failure of matrix is defined by this angle theta. Here what we see, the Ts and the sigma s, these are the static strengths, and this function here, the Ft, as we can see, it is related to the R ratio of the material, to the number of cycles, and another function, Fr, that is related to the fatigue behavior. So it's like, actually this Ft is more or less the SN curve, if we would like to see it in a very simplified way. So for different off-axis directions, these SN curves can be estimated. So these are off-axis SN curves, actually, can be estimated by solving this simple equation. There is another criterion from Fayaz and Elin back in 1990 something, I don't remember exactly. Yeah, 1994, I have it here. Whereas it was a very simple approach, a very, very smart idea, actually. Fayez and Elin suggested that you can estimate the off-axis SN curve of a material if you know one. Let me visualize this a bit. So if you do tests, and you remember the first material that we did tests at 0 degrees, 30 degrees, 45 degrees, and 90 degrees, and so on. So Fayaz and Elin said that if you know one of these, imagine that you know these 30 degrees, then you can estimate all the others by multiplying actually by the static strength difference. So that all the SN curves for them, they are parallel. And if you can have a kind of a master curve if you normalize all of them by their static strength. And to do this, they established this set of equations where as we see here, there is this. So for them, the new SN curve is this equation. And the terms that we see, so term F is the ratio of the strength of the material in the off-axis direction compared to the strength of the material of the SN curve that we assume that it is known. And this G term that we see also here, it is a term that relates the ratio of the SN curves that we try to investigate. Actually, for them, this is an SN curve prediction and also somehow a CLD, because it gives also the relation to the mean stress with this R, which is a bit, I would say, ambitious as a modeling approach, and you will see later on why I'm saying this. So after this, we had also other models. I will only describe here the concept of the failure tensor polynomial in fatigue, which is, again, this is a simple idea based on the failure tensor polynomial that we've seen before, the same Chai-Vu criteria. But then the idea here is that we can express as before in static, we can express the material performance by a simple polynomial equation with the same definition for the failure terms. But in this case, we can assume that the failure terms, so x prime, y prime, s, and so on, are not the simple tensile compressive strengths, but are the fatigue strengths. So this x prime, y prime, and so on are also functions of the number of cycles. So instead of defining doing a tensile test for this, we have to do an SN curve at this direction and define a complete SN curve. By doing this, actually what we have a failure criterion that is related to the number of cycles. And by doing this again, as we did before, we can solve for any off-axis angle, considering the material performance in the basic directions. So the normal loading, the transverse normal loading, the interaction between these two, and the shear loading in fatigue. So I'm presenting here some comparison of the failure criteria, and I will discuss also the sensitivity of some of them. Here we used again the material system that has been, so the database that was presented by Hassin and Rotem in their publication. They had a lot of data on unidirectional materials cut at different on and off-axis angles between 0 and 90 degrees. So here we see the results from 5, 10, 20 degrees in this figure. And in this figure, we see the results from 50, 15, 30, and 60 degrees laminates. For the, if you can you please stop playing with the slides? Okay. So if you remember, for the definition of the Fayaz and Elin criterion, what we see here, FWE, we need to define a reference curve that is used then to normalize the fatigue data of all the other curves. And in this case, the reference curve was the 15 degrees. That's why here in the 15 degrees, you don't see any prediction from Fayaz and Elin. So the other two criteria, FTPF, fatigue tensor polynomial in fatigue, and Hassin and Rotem criteria, used actually the 0 degrees fibers, the 90 degrees fibers, to define the X properties, 0 degrees, to define the Y properties with the 90 degrees, and they used also the 45 degrees for the CR properties. So that's why you don't see here the predictions for 0, 90, and 45, because they have been already used for the definition of the polynomial criteria. So the results are presented here. You can see that FTPF and Hassin-Rotem criterion are more or less the same everywhere. The criterion from Fayaz and Elin is the less accurate. In other cases, underestimates. In other cases, overestimates the material performance. And discussing the concept of or what we introduced before about the sensitivity of this Fayaz and Elin criterion, I plotted here the prediction for 30 degrees by using different reference curves for establishing the Fayaz and Elin failure criterion. The solid line is for 5 degrees, the dashed line is for 15 degrees, the dashed dot line is for 20 degrees, and dashed dot line is for a reference of 60 degrees. And what we can easily see here is, depending on the reference angle used, there is a very, very much different prediction. And what is also a bit disappointing is that there is not even a kind of trend that, for example, the 5 degrees is giving a data that are lower than on the others. 15 is the next, and 20 is the next, and so on. They are very, very much dispersed on the plane, and this does not give credibility to these calculations. So if we try to apply the failure criteria on the first material that we investigated in this during these presentations, and we compare here the FTP with Fayaz, you see again the comparison is not favorable for Fayaz and Elin failure criteria. Mostly it's FTP-F that is the more accurate. In this case, we used Fayaz and Elin with the reference at 45 degrees. We've seen when we try to predict 30 and 60, the prediction for 60 gives the data for 30, and the prediction for 30 gives very, very high data points. When we try to predict 15 and 75, the situation is a bit better. But again, there is an overestimation of the calculations. And then we can use the same failure criteria for multi-axial stresses. How this is applied is again because in the equations of the criteria we can even plot a triaxial stress state, so a failure locus on the 3D space. And here what we see is actually a slice of this complete failure loci. In the sigma, in this case, it was the material system that was used was a thin-walled, was based on thin-walled tubes. So there you see we talk about sigma axial and sigma hoop, the stress that is the tangential and the longitudinal stress on the material. So again, here the comparison of the two criteria for the normal stress and the shear stress of the shear loading of the tubes. Both criteria show quite good predictions. Again, if we go deeper in details, we see that the FTPF is a bit more accurate. And we have also another system from Fuji and Lin, the paper of Fuji and Lin, 1995, where they had the biaxial testing again of tubes under combined loading in tension and shear. So they had tubes that were loaded in tension and at the same time rotating, so they had shear. And in this case, we can understand the problematic that we have with the Fayaz and Elin failure criterion that is very, very much inaccurate when we depending on the reference. The data that we see in these plots are the same. Both plots, the experimental data are the same. The prediction from the failure tensor polynomial in fatigue are the same, but the predictions from the Fayaz and Elin failure criterion, which are those shown by dashed lines, are on the left side based on the reference. As a reference, they are based on the SN curve as 0 degrees. On the right side, the reference is the SN curve at 45 degrees, so in shear. And what we can easily see here is that on the right-hand side, where we have the data from shear as a reference, we have, of course, an accurate value here because this is the value that we used for the setting up of the model. But then when we try to predict the SN curve of the material under normal stresses, we are highly inaccurate. The line, instead of predicting for this 10 to the power of 6 number of cycles, instead of predicting value around 50, 60, predicts 100 plus. The next value that should be for the 10 to the power 4 of cycles, instead of coming to around 80, it goes to 120 and so on. And the same happens on the other side. If we talk about the figure on the left, where the values start, of course, at the accurate position because the criterion uses these values. And then on the other side, it predicts well for static loading, but then when we start introducing cycles, we start getting inaccurate, and the more we go in life, the more inaccurate we are, with the lifetime prediction for 1,000,000 cycles being less than 100% accurate. So we have a scatter or inaccuracy in the predictions more than 100% in this case. So the evaluation of the fatigue theories can be performed by assuming different or various, if you like, criteria, like the accuracy of the predictions for the SN curves at off-axis angles, or under biaxial loading, what we have already seen in the previous slides. The need for experimental data. So here, if someone looks the theory behind the criteria, the best one compared to between those that we compared is obviously the criterion for Fayaz and Elin, because for them the only experimental data set that is needed is only one SN curve, and the static strength data for any other off-axis angle that is needed to be estimated. But then if we mix this first and second evaluation criteria, we start having second thoughts, because the Fayaz-Elin criterion, we've seen that it is not accurate for all the cases. And actually the problem is not that it is not accurate, but it is not giving credible predictions. It is not consistent with the predictions. Either it is accurate for some cases, and it can be highly inaccurate for other cases. And this is what should be avoided in these cases with failure criteria. The third approach that we can have is to investigate how many assumptions the criteria are introducing, or if they are simply empirical equations that are fitted to experimental data. And in this case, from the criteria that we've seen, Hassin and Rotem introduced the assumption that the material fails either under fiber failure or under matrix failure, and they do not consider mixed conditions of failure, which is the case as we've seen in a lot of material systems that we are testing. And this is because they established their theory mainly for unidirectional composites, which for this type of materials, it is more or less acceptable to say that the material fails either under fiber failure mode or under matrix failure mode when we go off axis. But we've seen for example, in the material with the plus minus 45 degrees that we examined and presented yesterday or the day before, we've seen that the failure mode is mixed. We have fiber pullouts, we have delaminations, we have failures in the matrix, and we also have, depending on the loading, we can also have a failure of the fibers themselves. So these assumptions are nice, but they are not always validated by the experience. The same happens with the assumptions of the Fayaz and Elin criterion, that assumes that the material performance in fatigue follows the same degradation, the same rate, the same trend as the performance of the material in static loading, which again, it is more or less safe to assume something like that for unidirectional composites. But then when we go to other material systems, sometimes this this trend is violated. So it's not secure to assume this trend for any type of material. So then these materials that we are investigating are used for engineering structures. And we have already discussed, and we know that these engineering structures are very rarely loaded in constant amplitude fatigue. Usually the loads that are applied there in these structures are of irregular nature. So they are variable amplitude loadings that are applied to the structures, especially for structures that operate in the open air. And the question is if we can use this failure criteria to this kind of conditions as well. And of course, in this case, when we talk about anisotropic materials, we assume or we know that even uniaxial loadings can lead to multi-axiality in the stress fields. So there you see now how we bring together all the discussion that we had before about the stress multi-axiality, so the need to mix all the stress components of the stress tensor and evaluate the material performance considering all these components. We have also the variable amplitude loading, and we have to see how we can consider this variable amplitude loading to estimate the material behavior. And we have the material anisotropy that is introducing difficulties in the definition of the material properties. So in this case, we can introduce fatigue life prediction methodologies that can be based on different approaches. And the objective of all these methodologies, of course, is to estimate, to give at the end an index related to the fatigue life. Either we assume with this index that the material is failed, or we assume that the material is not failed. And what is also a request, if you like, is to quantify this assessment. It's not only to say material is safe or it's not safe, but it's also requested or desired to give an estimation of this safety or of this failure. Give a number saying, okay, your material has still 50% of the life, or if you apply these loads, the material will fail in the middle of your loading. So this is the quantification, and we can do this quantification with different ways. The simplest way that is done is either with this stiffness based failure criteria that we introduced in the previous slides, or by using this type of phenomenological failure criteria that we introduced now for stresses or strains, and the damage rule that is based on simple minor calculations. I suppose you remember the minor's damage rule that assumed that the damage that you have in a material is linear. It doesn't matter if you have damage created by a type of loading and another damage that is created by another type of loading. It doesn't matter which one occurs first. For minor, the total damage that you can have in this material because of these individual damages is simply the algebraic summary of these two. So this is the main assumption that we do when we use the minor's damage rule. So we will see now how we can apply our methods to actually analyze this problem. We have a material or a structure that is loaded under a variable amplitude loading. And the question is to give an estimation of the number of cycles to failure. So when this material will fail, or in the other way, if we know exactly the loading that is applied to this structure, to give an estimation about the safety of the material. Will the material fail at this loading, or it will survive? So if I try now to implement in this slide all the knowledge that we obtained these 4 days, actually 5 days from Monday and after, I would say that first I would do a cycle counting to transfer this variable amplitude loading to a block loading system that I can assess with the concept of SN curves, because SN curves is what I have in terms of material properties, and I need to know the loading in this format. The second thing that I need to do after this, so I have to perform experiments to estimate material properties. So if you see an inconsistency between these two plots, so between this one and this one, so the idea here is to do tests that will allow me to estimate partial damage factors for each one of these loadings. For this loading, and saying, okay, this one shows that in my spectrum, so in this spectrum, I have so many cycles of this amplitude and this mean stress, which corresponds to this SN curve. So I can come here and I say, okay, for this SN curve, my material will fail at 1,000 cycles. So here I have 10 cycles. So 10 over 1,000. This is my partial safety, partial damage estimated for this loading. I take this one, the second loading, and it might correspond to this SN curve. And for this SN curve, again, I have a certain value for this loading type. And if you assume that this one is at 80 megapascal maximum stress, again, we can say that from this one, I have another D2. And we can do the same if I have another loading that corresponds to this SN curve. I have a D3 and so on. So if we sum all these, we get the total D, which defines the material integrity. And according to Miner, if this is less than 1, then we are safe. So depending then how far from 1 we are, the safer we are. The problem that I see here is that I have probably SN curves that they do not correspond. We have counted data that they do not correspond. There is not a correspondence with any SN curve. And there, can you remember which tool we can use to estimate these unknown SN curves? If we know this, we know some SN curves for the material. Does anyone remember which tool we should show here to estimate unknown SN curves? You remember we discussed about this yesterday and the day before?
Constant life diagrams.
Exactly. Then here I have to talk about constant life diagrams, which, as we mentioned, they are established by using some known SN curves. So the idea is to do some experimental investigations, estimate SN curves, draw the constant life diagram, and then coming back to my spectrum, take a loading, so a block loading that does not correspond to any of these SN curves. It's not here, it's not there, it's not there, it's not there, does not correspond to any of these SN curves, but it belongs to this additional SN curve. And doing interpolation between the known values, we can estimate the expect. So actually, this red line corresponds now to a new SN curve that is related to this spectrum. So by doing this, then we can come back with this spectrum and again, calculate now a DI partial damage corresponding to this spectrum. So until now, we did cycle counting. We did, of course, experimental investigations in quasi-static and fatigue testing to define basic material properties. We developed constant life diagrams, which is the first modeling and prediction. So until here, all this part is modeling, experimental and modeling, experimental investigations and modeling of SN curves. And now here we start talking about prediction. And the first predictive model that we use is the constant life diagram. And then the second predictive model that we have to use is related to the failure of the material in multi-axial stress states. Because if we have multi-axial stress states, we cannot use directly the failure of the material according to the SN curves, because the SN curves, as you remember before, they correspond to specific fiber directions, specific material orientations. So there we can assume, in the case of the biaxial stress states, we have to use this kind of failure criteria to estimate the SN curve. We go further from this, we estimate the SN curve for different angles. If we don't have multi-axial stress states, we can go simply with these equations to estimate the number of cycles. But for the cases where we have multi-axial stress states, you see here with sigma 1, sigma 2, and sigma 6 in the material system, to estimate the number of cycles, we have to solve this equation. This is, of course, a nonlinear equation for NF, but it's not difficult to solve this one. And at the end, what we have either a simple SN curve or another simple SN curve that corresponds to multi-axial loading. So if we have this NF, again, this NF is used to identify partial damage. And as we said before, the final damage criteria that is used, the damage summation, is the linear damage according to the Miner's rule that says, as we described before, that the partial damage of any loading is the ratio between the number of cycles that we apply at this loading over the number of cycles that the material would fail if this loading would be applied continuously. And in this sense, we have a quantification of the material performance for long periods. So what I would show in this next slides is a kind of implementation of this theory to summarize actually these 4 or 5 days of fatigue life prediction of a composite material system. So coming back, discussing step by step, we have to do cycle counting. We've seen in the previous days that there are several methods for doing cycle counting. The concept is simple: to transfer a variable amplitude loading to block loading that we can then, as we've seen in the previous slide, we can then implement in SN curves and CLDs to estimate the partial damage corresponding to each one of these blocks. And there we have several methods, rain flow counting methods that have been introduced first, but then range mean methods, simple range counting methods. So counting in a cycle, each one of half cycle as half cycle of this amplitude and mean. But anyway, there are a lot of methods, and the output at the end is a kind of diagram like this. We call it also a Markov matrix that gives the number of cycles. So these histograms, if you like, correspond to the number of cycles in terms of height. And this diagram on the bottom shows the characteristic of the cycles, the amplitude of the cycle and the mean value. So there you can imagine that each of these cycle blocks correspond to a specific SN curve, because if we know the mean and the amplitude, we can define the R ratio of the fatigue loading. And then we can attribute this to specific SN curves. So for some of these, we have already experimentally derived SN curves. For some others, we don't have. And then we need to use the CLDs to estimate the SN curves for these numbers of cycles. And then the damage summation, as we said previously, can be either linear with Miner's rule, as we've seen before, or can be nonlinear. And these nonlinear damage rules have been introduced in the past widely. We have a lot of nonlinear damage rules that exist for different materials. And actually, what we can see is that these nonlinear damage rules are based on the basic concept of Miner, and introduce additional parameters to consider the material peculiarities. Actually, in this Marco and Starkey rule, this alpha I here is related to the stress value corresponding to each one of the blocks. For this Owen and Howe equation is a fitting equation to experimental data. It's a nonlinear damage rule, but you need to fit to experimental data. It starts with a C value equals to 2 and estimates A and B. And then iteratively, if you go and see the publication, they suggest to go iteratively and calculate the next estimate, actually the other parameters. So the implementation of these rules is good, and they work a lot, and they work very nice if you apply to the data. The problem of rules besides or beyond Miner is that they need additional data. So again, as you can imagine, if you have additional data to fit, then the accuracy is increased, but you lose more or less the potential of simple calculations that are conveyed by using the Miner's linear damage rule. So implementation of this theory that I've shown before, I did try to find in the literature some data that correspond to that give data for SN curves. Here we have SN curves for -1 and 0, and we have data also from different fatigue spectra of the type that you see here on the left. So Whisper X and Whisper fatigue spectra. So we can use this SN curve data to develop the CLD, and we can use this Whisper and Whisper X spectra to validate or evaluate the assessment potential of the theory. So we developed, and at the time I developed kind of small software to solve this problem. And as you see here on the left, the steps are the usual steps: cyclic counting, SN curve definitions, constant life diagrams, fatigue failure criterion, and damage summation with a Miner. So if we apply this, the first step is to convert, to do the cyclic counting, convert the variable amplitude loading to this Markov matrix that we set. So count actually how many cycles of specific range and amplitude we have. The second step is to define SN curves. So we have the experimental data, and then we fit SN curves. If you see here, exponential powers, Low-Sendetsky, Whitney, and so on. The stage is to analyze these SN curves with constant life diagrams, and then you can fit constant life diagrams and be able then to predict intermediate SN curves that can correspond to the cycles of the rainflow that are not corresponding to experimental SN curves. The next step is to take these values and do the prediction of Miner. So calculate from the failure criterion the remaining number of cycles, so the allowable, as we call, number of cycles, and then plot actually a line which gives you the minor sum and compare to the experimental data. And this can be done for the on-axis case, where you use the data for 0 degrees and you predict. So you use the constant amplitude fatigue data for 0 degrees, and you predict the variable amplitude fatigue data for 0 degrees. But then you can assume multi-axial stress states where you use the 0 degrees data for constant amplitude, and you predict the fatigue data for variable amplitude and other stress, other fiber orientations. And there you need to implement multi-axial failure criteria. And in this case, we have here some results showing that again the prediction is quite accurate with this methodology. We've said a couple of days ago about this sequence effect. So if minor is good or not, and we've seen that minor is not very good when we have a specific sequence, when we have a block loading which is at high stress levels, and then we go to a block loading of low stress levels, and we go to failure, and then we inverse this. We start with a low loads block, and then we go to a high loads block. Then it might be that the behavior of the material in these two different conditions is different, and then we can see that the material behaves non-linearly in terms of damage in these conditions. But experience that we have with a lot of materials shows that then if you mix these blocks, if you have a high, low, low, high, and so on, and you try to see which which damage rule fits better the material behavior in this case, then we've seen that the Miner's rule works quite well, because actually the sequence effect is dissolved in this a lot of different changes that we do in the one after the other. So the conclusion from this last presentation is that modeling is not prediction. When we talk about modeling, we use material data and we fit equations to this material data. While prediction means that we use some material data to predict the behavior of other material data. So try to keep this in mind when you also write your publications and when you analyze publication from others. We know now that we have methods for both material modeling and material life prediction. There are different in types of the methods. There's no unique theory yet. This is what we try to do in the, I would say, all around the world. People working with fatigue are more or less in contact to try to accept a uniform theory that can be used for many materials and many loading conditions. The problems that we have to approach this unified methodology is that experimental data are very, very limited. And there are also additional data. We know that there are additional data especially in commercial companies that are not shared because of many reasons. And this is a problem. We always push for open access databases, but it's not the how can I say, the open concept or the open mentality of people does not allow this. In European Union, by the way, all the research projects that are funded by the European Union necessitate open access publications and open access databases. This is a requirement from the funding body. But this is not the case everywhere, unfortunately.
I have one question here.
Yes.
You have shown for multi-axial stress state, so one of the failure criteria we can use where denominator can be a function of number of cycle and other variables. So there are people working on energy-based theories also, as well as some theories based on fatigue master curve. So as per your experience, which gives us a better comparison with respect to experiments?
I already said that there is no best failure criterion it depends on the material that we are using. We've seen these methods based on energy. For example, the criteria from SOCRI, the group of SOCRI. They are very good. They are very good. They're quite accurate for many material systems. But then again, there you have to consider or to think about the complexity of the data sets that are needed to implement the criteria. So the discussion that I had in a previous slide, where you have some kind of assessment criteria for the criterion itself. If it makes sense to use a more complicated criterion, it's not, I mean, it was a discussion before, but you can also see the same conceptual meaning here. If it makes sense to use a more complicated damage rule than minor, to improve a bit your data or not. I mean, if your data points are, your experimental data points are like that, this is not linear. So your behavior is not linear. But then I would say that a simple minor damage rule here is enough. You don't, theoretically, you should consider a rule like this, which is more related to your data if you push this a bit lower. And this nonlinear rule, it's more of this type. But to define these parameters of this rule, you need to do additional testing. So for this experimental data, I would say that a linear damage rule is fair enough. The same with the failure criteria. It depends on the complexity of the criterion that is used, the availability of your data, and the need and why you do this. It's always, for me, it's always the first question that I'm doing to myself when I establish a fatigue program, and when I try to establish a fatigue failure criterion, I say, what is my objective? What I need to learn from this, and this will tell you exactly which route to follow in all these cases.
Okay, thank you.
Okay. So I'm done here with the presentation.
Sir, I have a doubt. The software that is used for fatigue life analysis is CC fatigue software, sir?
The CC fatigue software is not released yet.
Is not realistic, sir.
No. Unfortunately, it is a software that I developed many years ago, but it's not yet open. The idea is to open up this software. We already have a kind of web-based version of the software, but it's not yet functional. It is functional for us. It works. I can use it to do all this analysis that I've shown here. These results are based on this software, but it's not functional for others, because there are actually some technical problems that do not allow the software to be used easily. So it's more a computer problem now, not an engineering problem for software. All the methods are implemented, but it's a computer problem that we have to work on that a bit more.
Is there any other open source softwares which can use for analysis, like fatigue life analysis? Any other open source?
I don't have in mind.
Okay, sir. Thank you.
Most of the softwares that you will get, even from the paid softwares, they are basically tailored towards some international standards. So they may be following some ASTM standard or some other standards, and the companies have made softwares according to those standards. But for unfortunately, as you rightly said, for research purposes, there is no in my knowledge, I could not find an open source or even a paid software which can help us in these problems, because we said that things are still evolving. As Professor Vassilopoulos said, the software is with them, but obviously because of certain reasons, it's not open to all.
Yes, yes. And the commercial softwares are usually less, how can I say, less complicated than these softwares that we are
Yes, they are actually closed-ended. Most of the commercial softwares are not open-ended softwares. They are closed, and again, they cater to mostly standards.
Yes.
For testing purposes, because they are mostly for fatigue, so they are for testing compliance purposes to certain standards. So, are there any more questions? So, I think there are no more questions. So, I take this opportunity now to thank our speaker, Professor Vassilopoulos, who has been here continuously with us for 5 days now. So, thank you very much, sir, for sparing your valuable time, which
Thank
I
you very
say
much, Raman.
is
It's
the
always a
most
pleasure.
yeah. This is the time is one reason why we couldn't get you here. Otherwise, we could have enjoyed your company in person here. But anyway, because of the time constraints, I understand it's a difficult task to travel. Maybe it will take 10 days for the 5-day course. So that is why we organized a virtual course. And if you have gone, if I try to sum up what we did in the last 5 days, is that in a way, as I said in my beginning introduction of the speaker, he has such a wealth of knowledge that 5 days and 3 hours a day is too small an time period for us to get it from him. There is too much of knowledge, and obviously he has tried to sum up his almost a lot of work into these 5 days for us, and which shall open avenues for which shall generate that spark in those students who initiate or who are working in the fatigue of composite materials. It's a very open area till date. From publications point of view, also, if you are interested about publications and then comparing that with the metal fatigue, we still find that this is a very open area in which the publications are possible. Obviously, you need the correct the hardware, the equipment, and basically the understanding of the phenomena and what your problem is going to be. So that way, it is a very, very open area and a challenging area for all the researchers. We have started with the first day on the basic history of composite material, history of composite fatigue itself. So we started with metal fatigue, went on to composite fatigue, and then the basic terminologies used for fatigue, understanding the fatigue behavior. Then we went on to experimental characterization, because till date, a lot of data, a lot of experiment data is being generated. So the database is coming up, and as Professor already said, that many of the databases are open source, but still many companies who are doing their own research, their database is still closed, so they don't disclose even their database. But they are doing a lot of work, like wind turbine industry, even aerospace is doing a lot of work on composite fatigue. But most of the databases are closed-ended, means they are not approachable for researchers as such. Even if they open up too late. It means maybe they may open up after 20-30 years, once that has taken the form of a particular standard. But that is the challenge that we keep on facing in this particular domain here. And then we had discussion about constant life diagrams, the phenomenological aspect of SN diagrams, what is the CLD diagrams, the effect of mean stress, and then the effect of what we call as R ratio. R ratio is nothing but telling us something about the effect of mean stress on the behavior of composites. We talked about creep fatigue interaction also, in which I also told something about our experimental observations regarding the creep-free fatigue interaction and its effect, and then where do we observe these interactions more frequently. We had a discussion about the adhesive joints, because again, adhesive joints are one of the important issues for composite structures. We need to join 2 pieces or 3 pieces together using adhesives. So, and there are other methods also of joining which many people are working on. Even they started with your conventional joining of composites also. But adhesives, to my knowledge, have proven to be more maybe easy and more compatible with the material systems of the base material or the substrate. And that is why we find that they have found more space when it comes to joining of these composites. We have talked about some computational tools also. I, along with Professor Vassilopoulos, we published somewhere in 2009 initial paper, which is now the same tools are being now named under, similar tools are being named under machine learning. It's actually soft computing techniques like NFIS, neural networks. Now they have further developed into learning models for machine learning issues, and then AI part is also there. They have named it, and many new techniques have been added. So that way, this was a course which we started with on Monday, and we are closing it today on Friday. After this, can say, because it's customary for me to thank the speaker because this is the last lecture from Professor Vassilopoulos that he has delivered for us. Afterwards, I have shared already with you a Google Meet link for a lab demonstration, which I will start, and I and Professor Singh will take that lab session for the speaker, for the participants. Already shared with the participants is a message regarding a quiz which will be held at 3:15 in Indian Standard Time. It is mandatory for all to appear in that quiz to answer. It's a very simple quiz which will be for 15 minutes. So you'll be given 15 minutes to answer the questions, which are very, very simple. So don't be afraid about the difficulty level. We understand that in a remote learning environment, and that too for a specialized courses, it is tough for everyone to come up to the same level of understanding within 5 days. So that is why the basic purpose of the quiz happens to be to check very, very basic conceptual knowledge of the participants, that what they have gained. It's a mandatory requirement under the GIAN program, and that is why it is mandatory for everyone to appear in that. So, with that words, I thank once again the speaker, Professor Vassilopoulos, for sparing his time and sharing his view with us. I'll request Professor Singh also, who is with me in my office itself, to thank the speaker.
Thank you very much, Professor Raman, and I take this opportunity on behalf of this institution to thank Professor Vassilopoulos for sparing so much time and delivering very nice and thought-provoking lectures on a very specialized area like fatigue of composites. So thank you very much, sir, for your time, and we would like that next time you are able to come to this place as before. So I also thank the participants for since we are ending the lecture sessions. So now you have to connect with the Google Meet link, which we have already been shared on the WhatsApp for the laboratory demonstration. Thank you very much. Thank you very much, Vassilopoulos, once again. Thank you.
Thank you. Thank you very much, both the organizers and, of course, all the participants for the patience and during this whole week, and for all this bothersome presentation that I had to deliver. I hope you enjoyed, and as you said, I would be very, very happy to be there again once if we find the good conditions and fortunately organize a bit the time better. The duties are becoming more and more, and time is less and less, and this is always unfortunate. So thank you very much again. I have to leave you now. I have to run to the next class.
Thank you.
Yes,
Thank you very much.
Enjoy the day and enjoy the weekend.
Okay.
Bye.
Thank you. Thank you, everyone.